Hi, I'm Mark Abbott, Dean of the College of Oceanic and Atmospheric Sciences at Oregon State University. The college focuses on graduate research, advancing the frontier of knowledge of the ocean, atmosphere, and Earth system, continuing to explore the edge, the interfaces between ocean and atmosphere, ocean and ice, land and sea, and deep ocean and sea floor. The college is one of the leading academic and research units at OSU and was ranked 5th nationally in the Decadal Survey of Graduate Programs by the National Research Council. The college research benefits the state of Oregon through studies of its coastal ocean, tectonic hazards, and atmosphere. Along with research, the college supports graduate programs in oceanography, atmospheric science, geophysics, and marine resource management. The Native Americans and Marine and Space Sciences program is also housed within the college, and it provides effective mentoring and educational opportunities for Native Americans. The college is home of the Oregon Climate Service, which provides an enormous range of data products and analyses for customers in the Pacific Northwest and beyond. The college remains at the forefront in the development and use of observational and analytical instruments. Observations of small-scale ocean physics are pursued with increasingly sophisticated instruments developed by college researchers. The emergence of ocean and atmosphere observing systems, including coastal observations and seafloor cabled observatories, afford new opportunities for sustained observations of our ocean and atmosphere. Our leadership in satellite remote sensing of the ocean expands to ensure that future instruments meet the needs of both the research community and those who could benefit by these analyses. We continue to expand and upgrade our state-of-the-art analytical facilities to provide access to both college and non-college researchers. The college continues to build on its interdisciplinary focus, integrating atmospheric sciences with oceanography and focusing on the interfaces between ocean and atmosphere. The college is uniquely positioned to study the Earth system, both in the context of global scale research and local processes such as those that take place in the coastal ocean. Each of these research activities highlights the college's continuing commitment to research and education, relying on state-of-the-art technology and facilities. Our newest facility, a clean room developed as part of the WF Keck Collaboratory for Inductively Coupled Plasma Mass Spectrometry, in collaboration with several industrial partners led by Hunt Air, places the college at the leading edge for a vast array of new geochemical analyses to support research in geological, chemical, and biological oceanography. I would now like to introduce the Keck Collaboratory Director, Gary Klinkhammer.
Hello, welcome to the WM Keck Collaboratory for Plasma Spectrometry at Oregon State University in the College of Oceanic and Atmospheric Sciences. Our facility has actually been here over 10 years, but the clean room part of this is just completed. In fact, it's still under development. So at this point, that makes it a little easier for this presentation because we can show you some of our technology in a little simpler way. What we do here at the Collaboratory is state-of-the-art science. In other words, we have equipment called plasma mass spectrometers. In this equipment, we actually have 4 of these very sophisticated instruments. And these instruments are capable of measuring basically all the elements on the periodic chart. So in this facility, we're able to look at the elemental composition of just about anything on Earth and tell you what that's composed of. Now, while that sounds very esoteric, actually there's some very practical applications of this kind of technology, which we'll get to in a minute. So let me show you some of the instruments that we have here at the facility. This is one of the 4 plasma mass spectrometers we have at the facility. They all operate under the basic same principle. They all have an argon plasma, as shown through, as you can see through this window. Now, the argon plasma goes up to about 8,000 degrees centigrade, so it's very hot. So anything we put into that plasma will be ionized, and we can measure the concentration of that element, or isotope, in whatever the case. This particular mass spectrometer is very good at resolving the mass. Each one of these mass spectrometers does a different job. The beauty of these instruments is they have an open front end. So we're able to hook up a laser to this instrument or a chromatograph, and this greatly improves the effectiveness of what we can do with these instruments. The downside of that is that it sucks in ambient air at the same time. So this kind of leading edge technology really requires that we work in a very clean atmosphere. Now let me give you one other example of a different type of mass spec that we have at the facility. Now this beautiful instrument represents the cutting edge of this kind of technology. This is the kind of instrument that we use for a lot of different things. It's very good at measuring the isotopic composition of materials. And this kind of instrument could be used from anything from measuring water quality to dating the age of the moon, for instance. So there's a whole suite of science kinds of projects that we can undertake here now with this kind of instrument. But all these instruments, as I said, all have this open front end. So they all require that the atmosphere that the instrument lives in is very, very clean. Now this kind of requirement is rather new. This kind of instrument was only been around a couple years. So more and more, this kind of application requires really good clean room technology. Now Dave Benson of Honair was the first one to tell us about the possibility of having this kind of controlled, focused, clean air environment. And that's really the topic of this presentation. So the fan filter units that are above these instruments focus clean air down to where we really need them, which is where the sample is introduced into the machine. So the rest of this presentation will be talking about the fan filter units that make all this possible. And so now we're going to go down to the studio, and I'll introduce the panel of experts who are going to tell us more about this great technology. Welcome. This part of our presentation is being brought to you live from the beautiful campus of Oregon State University. And what we want to do here, as I said, is describe the fan filter units in greater detail. Now, I'm just a scientist, right? So in order to be able to do this properly, I need a lot of help. And so what we have done here is assemble a panel of experts on various aspects of this project. So it took a lot of people to bring this technology to our facility. So let me begin on my far left by introducing this panel. This is Dave Benson, President of Honair, leading manufacturer in advanced airflow management. Next to Dave is Larry Hopkins, Engineering Manager for Honair. And on my immediate left is Jeff Hipp, Branch Manager in Portland, Oregon for Performance Contracting Incorporated. On my right is Steve Johnson, Territory Manager of GE Fanuc Automation, and Paul Selking, ECM Product Manager for GE Industrial Systems. Now, we have also set up something very special just for this presentation. We have an embedded reporter at the clean room. So at any point in time, and let Andy Unger here, who's our facility manager, introduce himself. Now, at any point in time, we can go to Andy and we can have some live input right from the clean room. So that's pretty cool. Now, I should also remind you that there is a question and answer period at the end of this presentation. So what we're going to do now is we're going to go around the table and we're going to let everybody discuss briefly what their input was into the project. And then at the end we'll have we'll start to answer some of the questions that are sent in. But don't let that stop you. As you saw from that address flashed up there on the screen, you can contact us anytime. Now you can address those questions to any one of us or our embedded reporter in the Clean Lab, Andy, or just leave the question open and we'll sort it out here. Let me start by saying something about how this project came about. And I should say that the Honair technology incorporated in our lab in our business is really unique and really cutting edge. And we can never thank enough the people that have had so much input into this project. Many of them are here. There's also a company called ChemWest that had a lot to do with the success of our project. So Honair, GE, and PCI put all this together, and we owe them a great debt of gratitude. Now, one thing it's clear even to me, being a scientist, is that the Honair fan filter unit is an ideal system solution for what we want to do, but I'm sure for what a lot of other people want to do out there and that require clean room technology. And there are a number of things that are involved in such a system solution. For one thing, up to 7, we can have the first slide, we can see that some of these, what a system like this can provide. For one thing, we can save up to 70% in our energy consumption. And of course, we work at a public institution, and these kinds of savings are incredibly important in the long run. Lower maintenance installation costs. You know, being a facility, we have limited resources to maintain such equipment, and it's really important that this equipment is robust. And we also have these greater control options, which are really important for what we do. And we're going to be talking to the GE folks later about some of those control options with this technology. We can say that this technology is the perfect solution for our application. And that's pointed out in this next slide. And that's true because of the exacting requirements that we need for cleanliness in this controlled environment for measurement of key variables. In other words, the work that we do, we're looking at extremely, extremely low levels. This is the whole world that we're living in, is unwrapping the levels that we can see and measure. That's where science is today. And that is key to where we're going in the future. So the lower levels we can see, the better. And this technology allows us to do that. Makes our job a lot easier. It's also, as stated in the last point here, the network integration and control requirements in a local and wide area environment. Now, Andy's going to talk a little bit more about that from our Clean Lab later, but it gives us the ultimate control of putting the clean air exactly where we're needed, and that's key here. Now, if we go to the next slide, we'll see some more broadly successful management of these conditions and where these things can apply. For one thing, they can apply to research and development facilities, which is what we are. But as we'll get on later in the discussion, we'll see that there's a wide range of other industries and research facilities that require this similar kinds of capabilities. Semiconductor design and manufacturing, biomedical and pharmaceutical production, bacteriological and viral control areas of food processing. And I'm sure there are a lot of others, ones that we haven't thought about, and I'm sure you guys out there have thought a lot about it. So there are a lot of areas that this kind of technology can have an impact. It's a tremendous advance forward. And if we go to the next slide, we can see that I just want to point out again the 4 primary contributors to our project. And this is the GE Industrial Systems, who have made the advanced motors and motor controls that go into this fan filter unit. GE Fanuc, who integrate the network controls, and we're going to have Steve tell us more about that. The Hunt Air, of course, came up with the fan filter unit design itself. And in our case, Performance Contracting Group, Inc., actually installed the equipment in our facility. So what we're going to do now is we're going to go around the table, and we're going to let each of our experts tell us more in greater detail about their part of the project. So now let me present Dave Benson and Larry Hopkins from Hunt Air, who will give us an overview of the room and the challenges they face when they're doing this project. Dave.
Thank you, Gary. One of the primary steps that we must undertake, like Gary described, is understanding the process that needs to take place within the facility and design the equipment to specifically meet the needs of the science or process that takes place within the facility. In this case, we had this next slide, please. We utilize extensive modeling to assist us in our design and application of our equipment. This 3D model is of one portion of the laboratory where we can identify the various different pieces of equipment that are in the space, identifying the cleanliness levels and requirements for each piece of equipment, and identify points of supply and return out of the space. In this case, we were architecturally limited by office space above and below the lab, and we were challenged to create a clean room in a space that was primarily built for office construction. We were able to utilize a low sidewall return for the return, as well as evaluate the exhaust ports from the ChemWest lab benches. Next slide, please. We were very limited in overhead space to incorporate the mechanical components that were required to achieve these objectives in the space. This slide is a depiction of our flush ceiling grid system that incorporated the fan filter units as well as accommodated the fan coils that are required to maintain the sensible cooling needs within the space itself. As Gary pointed out, the coverage in this case was not 100%. The overall requirement was a general Class 1000 with localized Class 10 needs. The fan filter units shown in the light blue are those clusters of fan filter units that were required to meet the objectives within the space. Next slide. Along with the 3D model of the space itself, we use extensive use of computational fluid dynamic modeling to help us understand the velocity profiles and pressure contours within the space so that we can assure ourselves, as well as the university, that we're going to achieve the results before physically building the building and turning the power on. Next slide, please. This slide is a model of basically the air streams within the space. We have the low sidewall return, as I referenced earlier, and the air is being introduced, and in this case the jet streams are particles being introduced into the model so we can study the airflow pattern within the space as it goes to the various different return points and exhaust points out of the lab itself. Next slide. And this part goes into a technical aspect of then our FFU, which I'll refer over to Larry Hopkins.
Thank you, Dave. At this point, we'll talk a little bit more about the FFU and what was physically changed, or what is different about this generation of FFUs that gives us an energy advantage. At Hunt Air, we're very familiar with the requirements of semiconductor, pharmaceutical, and biotech facilities in terms of cleanliness and extreme standards set for vibration, airflow, uniformity, and energy consumption. And next slide, please. So we took a look at the FFU unit, which is the prime mover in the space. This is basically what generates the air. It presents the air to the room, and it recirculates that air over and over again, basically continually purifying the air to present the clean process air. So at this point, we'll take a look inside the FFU and talk a little bit more about what we did to create the next generation FFU system. On the upper left of the screen is what you would call, what we could call a more traditional FFU unit, and these have been on the market for some time. And there's probably basically four components that make up the usual FFU design. We have the inlet at the top of the box where the air enters. We have the impeller or the fan section, and we have a fairly large baffle that's located below the impeller that's really serves two purposes. One is it creates a separate little plenum which enables the fan, it gives the fan the ability to develop pressure, and it also creates some noise control. The air then migrates around that partition and then is presented to the face of the filter, where it's ideally supposed to flow through the filter in a very uniform fashion. The FFU on the lower right of your screen is what we'll call the next generation FFU, and you'll notice that there's no separating baffle. We felt at the time that if we could develop a fan wheel that would pressurize the space, the plenum above the filter, and be low enough in noise and be energy efficient, that we could then reduce that restriction and increase the overall efficiency of the system. Next slide, please. This is the depiction of the results of that in terms of an airflow study. The image on the top shows in red tones higher velocity air patterns, which is really what we're trying to avoid. We're trying to present the face of the filter with a fairly uniform pressure gradient so that the air then just migrates through the filter in a well-behaved pattern, and we have a good uniform passage of air and we absorb the particles. The image on the bottom shows what we actually attained analytically, and it uses a fan system that's capable of pressurizing the plenum without the use of the baffle, the internal baffle. Next slide, please. This image depicts for us what might be considered an airstream. As it enters the top of the FFU, it migrates through the fan or impeller. It traverses across the target baffle in a traditional FFU. It makes a 180-degree turn and then is presented to the filter. As we can see, in this particular case, we can envision that there's quite a bit of static resistance to airflow and basically a wasting of energy. Next slide, please. In the next generation FFU, we eliminated the baffle by redesigning the fan wheel, and we ended up with an air pattern that comes into the fan wheel. It's distributed into the plenum above the filter face in a radial fashion and a very uniform fashion, which then proceeds down through the filter in a uniform manner. Next slide, please. As you can see, the type of impeller that would be used in a traditional unit, which is shown on the left, and the next generation FFU on the right are quite different in appearance. The impeller on the left requires the baffle to generate the pressure. And really the FFU that would be designed around that principle is going to have to overcome the static pressure that's inherent in the box. The impeller on the right will generate pressure without the use of the baffle. So really the effort here was to develop a cleaner air path, and to do that we had to develop a better fan wheel. We have one more slide, I believe. Two more slides. And this is the laboratory. When we started looking at airflows that were fairly low and low torques and low pressures, which are inherent in FFUs, we had to develop testing schemes that were accurate at those low volumes. And so here we had to develop our own AMCA 210 style test chamber and also the dynamometer on your right, so that each individual variable was tracked in order to come up with an improved product. The next slide. And this is probably the end of the story. What we have here are traditional systems shown as System A and System B, and what we achieved in the Hunt Air effort as on the left. Now those columns represent power, and the column on the left is represents 82 watts, as you can see, and the other two columns are up closer to 300 watts on the average. So essentially, to do the same exact job in a clean room, the next generation FFU requires about 70% less energy.
Thanks, Dave. Larry, that was great. It's a lot of stuff that I didn't know. And I really like those graphics. Of course, us scientists really like those models, you know, where you see things moving around. So we do a lot of that in oceanography as well. It beats the heck out of my hand waving in the lab about the air going around. And so that was very informative. Thanks a lot. Now, one thing that Dave mentioned that I had forgot to mention in my intro was the fact that this technology that we're talking about in the Keck Collaboratory, you know, it's only good for a very limited amount of time. Fortunately, the instruments are very expensive, but technology changes. And therefore, we envision, you know, as usual, that these instruments will last 5 to 6 years, and we'll be replacing them. And that's one of the very valuable things about this approach, is that we can change the organization of the lab, get a new instrument, change the positions of these fan filter units, and then be set to go. And that's really important in a public institution, that we can reuse and resources very efficiently like that. Now, and Dave mentioned another thing that's very important, and everybody should understand that this is a renovation project, that we're working in an old building here. And to get that grid up there was not something that was planned for when this building was built, let me tell you that. There's a lot of stuff up there, and it was amazing how much work that was to get that grid up there. And so that's really where our PCI came in. I mean, those guys did a tremendous thing in putting this all together. And so Jeff Hipp's going to tell us more about the construction aspects of the project.
Thanks, Gary. Like Gary mentioned, PCI performed the construction services for the clean room envelope, and if we could go to that first slide. Go to the slide, Bob. There you go. We've seen this before, but this is an artist's depiction of the clean room. And clean rooms are typically built from the top down, and this project was no exception. We start by installing what's called an interstitial support system, which generally consists of attachments to the existing structure, rods that drop down to support a strut system that is installed to conform to the layout requirements of the Hun-Air ceiling system. If we could go to the next slide. This is an actual interstitial above the ceiling. As you can see, it's very cramped. The interstitial at this clean room that we built for Oregon State had about 25% of that room. So there was a great deal of work went into a very small space. But once the interstitial system is installed, we install the Hun-Air grid modules and level them to the proper elevation, which is very important because the next operation is installation of the walls and doors. And the walls integrate directly into the Hun-Air ceiling system so that there is a laminar flow of air, plus these walls incorporated a sidewall return at the bottom of the wall, a very important aspect. We then performed a complete wipe down of the room and everything in it, and installed the fan filter units, blanks, and filters. Like Gary mentioned, flexibility in the clean room is very important, and the ability to move and change items within the clean room is facilitated by this ceiling system. You can put filters or the fan filter unit anywhere you need them very easily. The walls are also very easy to move around so that you can incorporate new tools, new rooms, whatever you need. And this photo that you're looking at right now shows a ballroom clean room. You can see it's wide open. You could put anything in there and isolate it or have it open to the entire rest of the room. Great deal of flexibility. Gary also mentioned that the limited head height in this clean room posed the greatest problems we had there. There was no room above the clean room ceiling to do work. To install that interstitial system, my foreman and my crew, my foreman Doug Young and his crew had to be very accurate with their layout. They did a great job. They hit every point they needed to because the attachment points on the Hun-Air ceiling system are fixed. We have to hit them, and that's laying out in 3 dimensions. Not an easy task, but they did a great job. If we could go to the next slide. This gives you an idea of the cleanliness levels in the clean room. This clean room was classified as Class 1000 with local Class 10 area, but this is typical construction type activities in a clean room. You can see that the mechanics are bunny suited up. They use a vacuum continuously. You have to be very clean. You can't touch things with your hands. Your hands are gloved. The oils on your hands leave residue that can in fact impact the clean room cleanliness. So the method of construction is very important. This clean room, like I said, had localized Class 10. That's a very high classification for a clean room of this nature, especially in a retrofit in an office building. That's pretty much the overview, Gary.
All right, Jeff, thanks a lot. I tell you, I was there every day. Andy and I were in there every day seeing what these guys were up to, and it was really unbelievable to see how much thought and energy went into creating that grid. So I think PCI really deserves a lot of credit, and they basically could do anything, in my view, that has to do with clean room construction. Okay, well, now of course the guts of the FFU is the motor, and that's where GE comes in. It's a very special variable speed motor, and it allows us to control the fan speeds, as we'll get to in a minute. But before we get there, let's talk a little bit about the hardware itself. So Paul Selking's going to tell us something about that.
Thanks, Gary. What I want to share with you is the 3 things. One, I want to share with everyone how this technology works in comparison to other motor technology that's used. Also, how the efficiency then is gained, as Larry and company talked about, because that is very important for the university here. And then thirdly, just talk about, in the motor itself, what is the technology we put inside that product to enable that. So if we start with the first slide, we can see the comparison here of the GE ECM technology versus the conventional induction motor technology. One of the first items is efficiency. This product operates at around an 80% efficiency, which is extremely high when compared to other induction motor technologies that range from 30 to 60% efficiency. That correlates for the end user into actually lower energy bills, which, as Gary pointed out, is very important here for the university. The second item on here that's also important for the original equipment manufacturer like Hunt Air is that one motor can be used in various FFU designs. With other motor technologies, it requires individual motors to be designed for every single FFU design, so again, provides the OEM with a little flexibility. Another benefit for the end user, in this case the university, is that this technology can provide them operation in constant torque or constant airflow. What that really relates to is if there's changes in ductwork or loading of the filters to change the static pressure, the motor can actually compensate for that all by itself to continue to deliver the airflow that the folks in the lab are expecting to get, that they got when they installed the product. The fourth item that I want to point out is the output capability. As we're going to see here in a little bit when we go to our embedded reporter and Steve gets a chance to talk about the control scheme, you're going to see that the output from this product is utilized to see how that motor is operating and if the fan filter is even on or off. So we're going to go to that a little later in the presentation, and I hope everyone finds that an interesting point because a conventional motor does not have that output capability. Let's expand on the efficiency a little bit and go ahead and look at the efficiency graph here. Two items that I want to point out to our audience on this. The first is the item on the far right of the page, which just shows the inherent efficiency benefit. The orange trace is the ECM motor, and the light gray trace up at the top is a typical induction motor. So at its rated point, all the way on the right-hand side, just the pure efficiency at the full load point is over 130 watts of efficiency, which is pure money and energy savings. But the real value of this product that brings the technology to life is that it has the ability to reduce power tremendously as you reduce the speed. There's 2 points on that graph that I want everyone to focus on. The first one is at 1,000 RPM. At that point in this particular graph, the product is using 280 watts of energy. The really interesting point here is if you cut that in half and go from 1,000 down to 500, the actual energy usage goes down to 35 watts, which is a 1 to 8 factor. So as you reduce the speed in half, the power goes down by a factor of 8, which is tremendous, and that's one of the features that Hunt Air has really leveraged to be able to deliver this, is the ability to operate this at a lower speed. If we go to the next slide, we'll see exactly the components of the product that enable this technology. And there's kind of 4 main ones. First, this product contains a permanent magnet inside it. That permanent magnet is what provides some of that inherent efficiency I just talked about on that previous slide over a standard induction type motor. Second is this product has a ball bearing construction. That's very critical for reliability. As Gary has talked about, yes, this may only be used with this setup for 5 years, but the fan filters actually hopefully will have a much longer life than just the life of the equipment in the room. So with the ball bearing construction, this product can actually have that long life that the end user and the original equipment manufacturer is looking for. Third benefit is that this product has an onboard microprocessor, and this is really the guts of the product. It's the heart of what brings this product to life. It enables the interaction with the control system. It also enables the end users in the lab to make the changes in speed and to do the work that they need to do on the product, and is really the key item that drives this product as it continues to go. If we look then at the fourth item, it's the development software. The software is what allows both the end user and the OEM to tune in this product to work for the end user's application in the clean room. With that, I want to just wrap up by saying that the efficiency and control flexibility of this motor has enabled us to deliver over 3 million of these units out into the world in various applications to deliver high efficient energy savings, and also air moving. Thank you.
Thanks, Paul. That was really impressive. I mean, you really drove home some good points there. One thing that I thought of was the time when I was talking to Dave Benson the first time about, and he mentioned the fact that there might be a new motor out there, a new technology that we could use in the clean room and you could control it digitally. Of course, I just went nuts on that and immediately wrote Dave an email saying, oh, sure, we want to do that. We want to be able to control these motors. And that would be really a cool thing to do. And so since Dave's a go for it kind of guy, he put it all together and now we're at where we're at today. And part of the key to that system is really the software control. I mean, that's really important for us, and I'm sure there are a lot of other users out there, potential users, that could use this kind of capability as well. The idea that you can adjust the speeds on these fans is really a pretty neat thing. And Andy later is going to tell us some reasons why that's important for us, but like I say, I'm sure there are other people out there that could appreciate this as well. So we're going to delve into that aspect of the technology here a little bit. And Steve Johnson's going to tell us a little bit more about the software that makes this go.
Thank you, Gary. By using the low-end standalone programmable logic controller along with a 4-wire network, we stayed flexible and distributed. Now let's look at some of the slides involved in it. The small footprint, low-end GE Fanic Nano filled the needs with what we had with that. Next slide. The strength of the GE Fanic Nano is the high-speed counter input, the PID software capabilities, and the pulse width modulation output that Paul talked about with the programmable controller controlling the motor. With that, we can set the motor speed, we can maintain the speed with the PID algorithm, and actually confirm actual speed back to the clean room operator with the Simplicity HMI software involved in it. Some of the control benefits and options that we had in this include a development tool chest, which allows the designer to create one fan filter unit control and cut and paste that into all the other systems. The common database allows the designer to develop the logic from the Nano software and then use the same database to create the graphics associated with it. Most systems require 2 separate databases to do that and twice the work. The connection to a common protocol allowed us to connect up the small nanos to the software and do the control with it. And then of course the fourth thing was the internet connections allowed us to monitor and control inside and outside the clean room to where Andy could be in his office adjusting some of the fan filter units with it. Next slide. Simplicity Machine Edition software is a window-based software, and it consists of a development package and a runtime package. Simplicity Machine Solution gathers data from the GE Fanic Nanos in the ceiling of the clean room and displays that information on a touch screen that Andy will show us here pretty soon, which we'll see here in a few minutes with this thing. Machine Edition also then broadcasts this information over the internet and allows it to be monitored and possibly controlled from other areas as we go. Next slide, please. These products are used in many other industries as are shown here with it. And now let's take a closer look at the operation in as Andy shows us some of the control aspects.
I'm here at the Hunter fan filter control system control unit that uses GE Simplicity software to control the fan filter units. And what we're showing over here now is the general overview of the room layout. With on the right side we have the wet lab for processing samples, and the left 2/3 here is the area where we have our mass spectrometers. We have several panels that are part of this control system. As I said, here's the layout, the overview that shows the status of the fans and the locations of them. And we can also switch here to a different panel here that now shows in a more digital format the fan conditions. We have a fan status display here that shows the off-on of each of the fan units, list them all individually. We have a speed readout that shows the RPM of the fan filter units. and we can stop these fan filter units from this screen. Having this individual control of all these fan filter units is really beneficial for us because it allows us to concentrate clean air over the instruments and also slow down the amount of air movement in certain areas, for example, in our balance room, where we're running the lowest speeds. In addition to that, we can also control fan filter speeds in our sample processing area where we want more clean air flowing, especially near the fume hoods.
Thanks, Steve. Thanks, Andy. Okay, with that, I think that we've been around the table. We've heard what our experts have to say. Get those questions in. There's the address again. And so it's time to move on to Q&A. So we have one question here already, and it's kind of an interesting one, actually. Are there FFUs anywhere else in the clean room other than the ceiling, which is the obvious place that you should go, I guess? Okay, I think we should need to go to our embedded reporter for an answer to this question. Andy, you there?
Yeah, I'm here, Gary. Yeah, that's a pretty good question here. And in addition to the units in the ceiling, we have a need here for having fume hoods for processing our samples. And we had Chem West of Portland, Oregon here build us this all polypropylene clean hood, and we refer to this as a clean hood because in addition to the fume extraction capability, it also incorporates one of the Hunter fan filter units on top that puts down a whole blanket of clean air over our working area so that when we're diluting samples out here, we know that we have clean air over our samples.
Well done, Andy. Don't mess anything up there. I'll be back there in a few minutes. Now, let's go on. There's a couple of questions here for GECM. Question number one, how does the efficiency compare between standard motors and variable speed ECM type motors at reduced airflows? That's pretty technical.
The best way to describe that was shown on the graph earlier, but to basically sum that up, it's two things. One is the efficiency of the product versus typical motors just is inherently more efficient, and that's typically 10 to 20% points of efficiency on that. In addition to that, though, this question's interesting because it talks about the reduced airflow, Gary, and that's really where the power of the product is. When you reduce that airflow, and which is in fact typically reducing the speed, in that case, the actual energy is reduced by a factor of 8. So when the energy that was used previously is used in an ECM, it's 1/8 of the amount of energy that is used at those reduced speeds and really provides the end user, in this case you guys in the lab, a real benefit in terms of your energy bills because you have one of those motors in each one of those fan filter units.
Right, good. Here's another one. This guy is thinking about if he was reconfiguring a clean room layout with ECM equipped FFUs, what kind of issues would he face?
Yeah, let me talk a little bit about changing the ECM in that, and then Jeff might have some input too from what's involved in the construction to change around the room. From the FFU perspective related to changing the motor, the great thing about it is because it's integrated in the Hunair system with Steve Johnson's control, this product can be actually changed for its speeds and therefore its airflows and torques that it produces simply by the software that Andy showed in the clean room earlier. So by going to that software, picking the individual fan filter unit, that fan filter can then be selected and changed for its output to produce the airflow that's needed when the room is reconfigured. So if a piece of equipment gets changed out or you put a new piece in, Gary, you can actually change the FFU to provide the airflow it needs in that area. Obviously, the motor won't physically pick it up and move it, but I'll let Jeff just give you an idea of changing that.
Well, that's one of the benefits of the Hunair sealing system as well. It's a urethane gel sealed system in that the FFU sits in the gel track and that provides the air seal. To change that location, just pick it up out of the seal, move it to the next location, take the blank that you replaced it with and put it back in the place where the FFU used to be. Very simple to reconfigure a clean room with this system.
Thanks, Jeff. Maybe we could go to our better report there, Andy, in the clean room, and maybe you could point us up at the ceiling and see what one of these grids look like, and over the instrument. Can you do that?
Yeah, Gary. So I'm right now pointing at one of these 2x4 face cleans, and the interesting thing is here is you can't tell when you're looking at these which ones is a blank panel, which one is an FFU. But of course we know where they are. But if we wanted to change that, we pop out the face clean, and as Jeff was saying, lower the fan filter units and put it in its new place, and pop back up the face clean, and it looks like a finished ceiling again.
It's got to be easy. Even a bunch of scientists can do it. Let's face it. Okay, so let's move on. Here's a question I think maybe Dave Benson might want to field this one. What are some of the elements of the clean room design that make the OS installation and configuration unique? You could probably talk about a couple days on this one. Dave?
Well, probably the element that was most unique about this application are some of the items that we've talked about, in that this was a very old facility, and architecturally there was not the space that we would have in many of our newer installations and facilities. The system is designed for a Class 1, down to Class 1. In this case, we're Class 1000 with localized Class 10, but we had approximately 25 inches to incorporate the sensible cooling, the fan filter units, and the ceiling grid around walls and shapes within this old facility that wasn't necessarily at right angles to each other. So it was a challenge to us from a manufacturing standpoint, and to Jeff and the PCI crew on getting it installed.
Thanks, Dave. Larry, here's one that you might want to tackle. How do sound and vibration levels within the OSU facility compare to other facilities using traditional designs, and how do they compare to industry standards?
Well, sound and vibration levels in clean rooms are very, very important. In fact, sometimes architects and engineers completely isolate a facility like this, or isolate it from Earth in certain respects, to insulate it from, say, train pass-bys, roadways, and so forth. So we have to be very careful in designing the FFU not to generate vibration that's going to be transmitted to the grid system and subsequently to the floor. One of the advantages of a smaller fan that's used in an FFU is that you have lighter masses, lower lower velocities on the fan wheel tip speeds, and you can control your vibration in the cabinet much more effectively than you can with a very large piece of equipment. So in terms of where the facility can operate, we feel very comfortable about putting this technology in the most stringent environments of Class 1 or better clean rooms.
That's great. Yeah, very good. You said, I feel like the old Groucho Marx show, you know, you said the magic word, mass. We like that word, mass spectrometers. Okay, so let's talk a little bit. Here's one that maybe Steve could answer about the software. What can you control using the Simplicity Machine Edition software?
The Machine Edition software actually focuses into the programmable controllers and reads register information within that. So you can set speeds and read speeds in and out of the individual controllers onto a touchscreen computer and let the operator see that in real information. It may be in RPMs, or it may be just a simple start-stop indication of what's going on in the motor, but you can read that out and you can actually analyze what's going on with the system in it and change those either individually or as a whole group.
Thanks, Steve. Hey, maybe we should go to Andy again, and he could go back to the touchscreen, Andy, and maybe talk a little bit about how we intend to use this Simplicity software.
All right, thanks, Gary. I'm back over here at our touchscreen panel, and as Steve was saying that we have individual control here of these FFUs, and we can turn them on, turn them off as we need, and change the speeds on this screen. So it's really pretty powerful, especially like in certain areas, specific areas when we really know what we want to have clean air in the fume hoods. We can turn up the speeds, and it's pretty easy to do. And over our mass spectrometer, which and we'll have samples there on which we're trying to measure parts per trillion or parts per quadrillion quantities of metals. It's really important to have clean air in those locations, and we can go in there and we could turn down the speeds when we're not using it in that capacity and for energy savings, or we can turn it up for maximum capability when we need that for the best analytical data.
Yeah, I guess you could see from the screen there that Hunt Air has taken the Simplicity software and kind of adapted it. It's kind of specialized it for our needs, but that's pretty cool. Thanks, Andy. Now, here's another one that Steve might be able to deal with. How do you network your small PLCs, nanos, to control the fan filter unit?
Yes, that is done through a serial port on the Nano itself, and you can set it as, some people know, Modbus RTU serial, and you connect 32 of them up on a 4-wire network. You go ahead and connect that into an Ethernet port so that you can jump on the actual TCP/IP network of the facility, and you bring that right into Simplicity and read the data in and out of the different individual programmable controllers into the Simplicity unit, and thus giving them the flexibility if they do want to move the ceiling grids around, they can do it by just moving those 4-wire conductors around.
Okay, thanks, Steve. Let's jump over now and ask Jeff another question. Is this a typical type of project for PCI to build?
It is, Gary. PCI is one of the largest specialty contractors in the nation and one of the largest cleanroom contractors in the world. We provide construction services ranging from cleanroom contracting, design build, critical environments, and commercial construction activities as well. We have branches located throughout the U.S., approximately 90 branches. We can be there.
Oh, thanks. That's good to know. As long as we're talking about quantities, maybe it'd be good to know how many of these units are on the market. I'm not sure who should field that question. Somebody from Hunt Air, I would assume.
Well, sizes of projects vary from the size of your lab, Gary, to a meeting that we were in just last night that would have over 3,000 of these FFUs with the GE system incorporated in a Class 1 facility. I think, as Paul pointed out, there's over 3 million of the GE fan components throughout the world installed, not all of which obviously have been within the clean room itself. But projects do range from hundreds to thousands of units on any given job.
That's impressive. That's a lot. Let's see, here's a two-part question. Maybe Larry could do this one. How does the OSU cleanroom design using the Hunt Air fan filter unit compare to traditional cleanroom designs in terms of energy consumption?
Well, the traditional cleanroom design could take a number of forms, Gary. The goal is to provide a uniform piston of very clean air across the process surface in the cleanroom environment. We could use large externally mounted fans recirculating air through return paths and distributing that air through ducts to the face of the HEPA filter. That would be a traditional system. Those types of fans could range from axial type fans to centrifugal plenum type fans. And so I guess to make sense of all that is that there are some pretty efficient fan systems out there that can be employed. Now the amount of energy that is used is largely dependent upon the path, the airflow path. So the longer we have to throw that air and the more things that we have to put it through to get it to the process, the more energy it's going to take. And so one of the things that the fan filter unit does in this particular case is it minimizes those losses. And so I would say probably the prior graph showed pretty well the range of energy that might be required to pump air through a clean room. In this particular case, it could be, let's say, as low as 90 watts for a Class 10 clean room up to about 300 watts, depending on the system that's chosen.
Actually, this was a two-part question. I think you answered some of this during your presentation, but historically, what's the trend in the clean room industry for adopting this energy-efficient technology? I assume that's what's happening here.
Well, that's a pretty interesting question, and Dave and I have been in this business for quite a while, and we've seen some inflection points. When we first got into the clean room business, people were using what we call forward curve fans, belt drive fans, traditional equipment that would be used to circulate air in a commercial building, let's say. to drive air through filters to create clean rooms. And somewhere in the mid-'80s, Dave and I came together in a company, a local Northwest company, and we developed the use of a plenum fan, which gave us the ability to compress the footprint and create that air path in a more efficient manner. And we created a kind of a breakthrough at that time, and we lowered the amount of power required to circulate that air. And it became pretty much the standard in the industry. And these were distributed recirc units, we'd call it. And so most large semiconductor or pharmaceutical companies have quite a few of these in play. In the mid-'80s, we also developed a new fan at that time, which gave us an additional benefit. I'd say in around 10 years later, we worked on the fan again, and others have, and they created, let's say, another notch, another improvement. And so now, today, going into year 2003, we basically have kind of gone the next step and taken the next crack at it. So what we see today is, in some ways, a refinement on what we had in the past, but it's also coupled with the GE motor technology that really gives us the ability to say that we've made a breakthrough.
That's really interesting. You know, being someone out of the business, it's really really amazing to think about. At one point, we could have had all these belts whirling around above our heads. It's pretty incredible. But and I should say, just from a general point, that this technology has really been amazing to us. I mean, you wouldn't believe what scientists have done over the years to try to get clean air. I mean, we're talking bubble gum and plexiglass here, and so having this kind of state-of-the-art thing coming together with the science thing is really a large part of what makes it all go around. And we're going to be able to do a lot more high-quality science, cutting-edge science than we could have before. So for far as me, of course, that's important. For other people, other things are important. But this technology has a wide application. I think that's really the take-home message we want to bring here, is that when it's easy to imagine the breadth of the users that might use this kind of technology, and I'll say that of course we're always open to anybody coming to our lab, either on our website or emailing us directly, and we'd be happy to share our thoughts about the technology. And because we think it's great, we think it's perfect for us, and I'm sure there are other people out there that would think the same. So at this point, I think we should ask anybody on the panel if there's any last words they want to come up with. We can go back to our embedded reporter one more time. Andy, you there?
Yeah, I'm still here. I did think of one more thing I should add. If we go back up to the ceiling, we have one panel here that doesn't have the face clean in here. So if you look up here, you can see there's just 6 clips that you turn, and you just turn those clips, drop the blank pan, and then the fan filter unit goes up the same way. It's just held up by the 6 clips. So that sort of shows how easy it is to make those changes.
Andy, go back to Andy for a second. I want to say just one last thing. Could you not say anything for a second? I know it's hard. Don't say anything. We're trying to hear how what the lab sounds like. See, it's actually a very comfortable lab to work in. That was my point. I mean, the lighting is great. It's just a really nice feeling to the lab. It's really come together very well. Okay, back on me. All right. So if there are no other questions, I guess we're out of them. The panel and myself say thank you very much for joining us, and have a good day.